Assalamu alaikum gentlemen. Today the topic which we are going to study is three-phase transformers in the power systems analysis course. Regarding three-phase transformer, it has the basic working same just as the single-phase transformer. The basic fundamental working principle is same. Like in the single-phase transformer, there is an option that it can step up the voltage and step down the voltage, right? So in this particular case, the three-phase transformer can also boost it up, or it can put it step down. So these two options are already available with the three-phase transformers. However, in the single-phase transformer, what we have only there is single phase, right? The single voltage waveform is already there. But in the three phase transformer, what we have the three voltage different voltage forms, and that are known as red, yellow and blue. And across the red, yellow and blue phase, there is 120 degree of phase difference exists between each of them, as I have told you earlier. So coming on to the main point of the three-phase transformers, what we have three-phase transformers. In three-phase transformers, what basically we have the two basic options. That first of all is to connect the three single-phase transformers. In order to connect the three single-phase transformers, what we have, we will take the three transformers and connect them with a neutral in the case of Y connection, or we can make them interconnected in the delta format, right? Y is also known as Y connection is known as star connection, whereas delta connection is known as mesh connection, right? So in this form, we can further say that for three phase, and the second method is to construct a single platform for three phase transformer. Means what we have a iron platform or a copper platform. The iron platform is the best one for construction of a three phase transformer. Then we are taking the single platform for making all three phases interconnected. So the iron platform will be enough, and across iron platform we can construct a single platform for three phase transformer. Now elaborating the case 1, what we can say that in case 1 we have two single phase transformers that are interconnected in delta format, and then they are connected to third phase, third single phase transformer in delta connection, right? This is first phase of connections, right? And that is first first kind, in which there are two single phase transformers that are already connected in delta format, and then they are connected to the third single phase transformer in delta connection, right? This type of connection is known as delta to delta connection, right? However, if we can consider it in the further procedure, we can say that there are several types of connections. What can we say that we have, if the first two transformers are connected in Y or in the star shape, right, and then they are connected to the third one in the delta, then this format is known as Y to delta connection, right? Y to delta connection. And in the next case, what we can say that if the first two transformers are interconnected in the delta format, and then they are connected to the third one in the Y phase or star phase, then we can say it, we can call it delta to Y connection. However, if the two single phase transformers are interconnected in the Y phase and then they are connected to the third winding, to the single phase transformer across the third winding in the Y format or star format, then this can be known as star to star or Y to Y connection, right? Y to Y or star to star connection, right? It is better to write star to star, but I have mentioned it in the symbolical form, right? So after it, there is another thing for the case 2. What we can say for case 2, a bank of three phase transformer can be replaced we can further elaborate it as that a bank of three single phase transformer can be replaced by a single platform of having iron structure, right? We can say it just like this, right? I'll provide you with this page later on. After it, we can watch its major construction, that how it can be constructed. So in order to construct it, we can have the two options for its construction. Either we can design it in the core type construction, or we can make it in the form of a shell type construction. What is meant by core type or a shell type construction? In the core type construction, what we have a three phase and three leg core structure, whereas in the shell type construction we have three phase but five leg core construction or core structure, right? We can draw it. It can be drawn just like this, that A to A type, right? Then B to B type, and then C to C type, right? So we can say that we have this thing, right? And this outer can be drawn just like this thing, right? And this one is here, this is just like this, the B connection, and then this B to C connection, right? This is basically core A, this is core B, and what we have core C here, right? So this is basically this structure in which this magnetic flux will move across this type, right? When it can move in this type, then it is called as let me tell you that this thing is line of magnetic lines of flux, right? This is basically a three leg core structure. Here we have. Now if we have to design a three-phase 5-leg core structure, how it will look like? It will look like just like this. Let me draw it. A, B, B, and then this one is C to C, right? So the outer core will be, what will be the outer core? It will be just like this, as I have drawn in the previous case. It will be just like this thing, right? Whereas how the inner core will look like, it will have 5 legs actually, right? So this thing is just like this one, B to C, and then and here it is having just like this structure. Now you can watch it that it has 5 legs, 1 2 3 4, and this one is 5th one, right? So I can draw the magnetic line of forces here just like this one, right? And here we can have just like this thing. This structure is known as three-phase 5-leg core structure, right? So in the 3-limb core type as shown in this figure, the three-phase transformer is most common method of three-phase transfer. This three-phase 3-leg core structure is the most common method for three-phase transformer construction, as it allows the phases to be magnetically linked. ठीक है? How it allow phases to be magnetically linked. Okay. So the flux across each limb uses the other two limbs for its return path, with 3 magnetic fluxes in the core generated by the line voltages. And as you know that in this case there are 3 phases, so the difference between each phase is 120 degree, right? Phase difference is 120 degree. You already know this, as I have told you in the previous lecture. So the flux in the core remains nearly sinusoidal, producing a sinusoidal secondary supply voltage, right? So this will be in this method. However, if we construct this three-phase 5-limb type, then it will be relatively heavier, right? This structure will be relatively heavier, and then it also will be expensive to build. This shell type structure of 5 limbs will be relatively expensive to build. So that's why we often prefer this structure, right? So the 5-limb cores are generally used for very large power transform, very large power transformers. This structure is relatively very higher, so we cannot put it in at the very high altitude. We can place it on the reduced height, relatively reduced height, and a shell type transformer core material, electrical windings, steel enclosure and cooling are much the same as for the larger single phase transformers, right? So coming on to the topic again, what are the benefits of case 1 and case 2? We will note them down, right? Just like the case advantages of case 1. What are the major benefits of case 1? That replacement of a single phase transformer or a single unit is possible, while other two units will be keep on working on relatively low voltage, while two other units will keep on working at reduced kVA, or you can say they will be operate at low voltage, right? What are the advantages of case 2? Now we can say that what are the advantages of case 2, but before describing its advantages, let me tell you that the this single phase unit, that in the case if there is a fault in the single phase unit, then you can replace this one by using then you can replace this unit, or you can remove this unit having the fault in it, and after removing this fault, then you can incorporate it again into the unit. When we have this single phase transformer replaced, then what we can call it, if we have removed the faulty single phase transformer, if we have removed this faulty single phase transformer and two single phase transformers are working, and two single phase transformers are working, then this type of transformer is then this type of connection is known as open delta, right? In this particular case, when we have one single unit is removed and the two other units are working at the reduced kVA or low voltage, then we can call this one as open delta connection, right? We will describe open delta connection later on. Now coming on to the case 2, what are the advantages? That it takes considerably less space due to its reduced size. You know that controlling the three single phase transformers and space taken by each of them is relatively larger, so the overall total space is higher as compared to a single iron platform in which there are three phases are incorporated and amalgamated, right? So less space due to its reduced size. After it, the other thing is less iron is required, so less iron is required as for the single platform, so they are cheaper and economical, right? So this is its another benefit. Now in case 1, a single faulty unit is removed and two single phase are working. We know that it is the open delta connection, and in this case 2, then less space due to its reduced size, and less iron is required, so it is cheaper and relatively economical. uh, Now coming on to its construction, first of all we will make its construction. Let's draw a figure of a star to star connection. Let's say when we will draw the figure of a star to star connection, then it will just look like this thing, right? Here it is, and then here it is, and here is the third one, right? Just like this we can make it on the other side. What it will do, it will be just like this thing, and here we have this thing, and now here this connection is neutral, and also here we have another neutral, right? This is known as N, and here we have these terminals. So this is our first figure, and let me draw its equivalent figure. Its equivalent figure will be just like here, this thing, and this one, and just like this we can construct this figure on the other side. Here we have this thing, and now this one, and here we have this thing, right? So this is x1. Let me tell you that according to the American standard of designating terminal, we have the the terminals present on the left hand side, that is high voltage side, are represented as H, whereas the terminals present on the right side, I mean to say on the low voltage side or on the secondary side, are represented by X, right? So this is H1, H2, and here we have this H3, and likewise what we have here on the secondary side, this is x1, this is x2, and here it is x3. Now also what we can say, that the terminals present on the primary side are denoted with the capital letters of A, B, C, X, Y, Z, L, M, N, or whatever you want to take. I am preferring writing A, B, C here. A, B, and C. The terminals present on the secondary side are represented with the small letters, right? And along with the small letters, we can say that don't ever forget to mention the polarity here, as most of the students often forget to mention this polarity. These dots are showing that these are having the same polarity, right? Likewise, we will do just like this, A, B, C, and here we can say that A, B, and C, and just like this we can write these terminals as x1, x2, and x3. Here we can say that h1, this is h3, this is h2, and here we have h1. This is basically Y to Y or star to star connection. Okay, uh, you can see that both the figures are almost same, both the figures except the neutral, right? So this is the basic thing. Now in y2 I have already described that in y to y delta transformers polarity is marked such that the neutral voltage to neutral from H1, H2 and H3 stay in phase with the voltage to neutral at terminals X1, X2 and X3. What? In y to y or delta to delta transformers, the polarity is marked such that voltage to neutral from high voltage terminals, that is H1, H2 and H3, stay in phase with voltage to neutral at terminals X1, X2 and X3, right? However, as you know that across the delta windings we have the no neutral point. So if we don't have the neutral point, then what can be act as neutral? Under the balanced voltage conditions, ground can be served as neutral in this particular case, right? So we can write it down so that we can include it into the notes. However, as you know that delta windings have no neutral point, so under balanced conditions ground can be under balanced conditions ground can serve as neutral. Ground can serve as neutral, right? As you know that for phase voltage to line voltage conversion is given by the formula phase voltage to line voltage, right? This whenever we have this type of conversion, then what we can say that it is just like this Vp is equal to 1 over square root of 3 into VL, where this Vp is phase voltage and this VL is line voltage. Okay, so during Y or delta connections, what we can say that during Y or star connections we have the current IP is equal to IL and IL is equal to IP. It means that the phase current or line current remains equal, whereas in the case of voltage it used to have different variant. Vp is equal to VL divided by under root of 3 and VL is equal to under root of 3 Vp, right? We can say it is just like this one. Actually I am writing it in this form, that it is one time I am writing in the phase voltage, the other time it is across the line voltage, then it is phase voltage, and then it is line voltage, right? Sorry, I have I have not delivered it properly. That is, phase current is equal to line current, or the line current is equal to phase current, and then this phase voltage is equal to line voltage divided by square root of 3, and likewise it will be VL. It means line voltage will be equal to under root of 3 into phase voltage. And during delta connections, we have this phase voltage and line voltage will be equal to each other, right? Just like this. Whereas the phase current will be equal to 1 over under root of 3 into IL, and here line current, if written in the form of phase current, it will be equal to under root of 3 into IP, that is phase current. Okay, so if one asks you to determine the star to delta turns ratio, how we can find the turns ratio? There is a very simple and very basic formulation for it. Star to delta turns ratio, it will become TR star to delta, it will be equal to ratio of turns on the primary side to the turns on secondary side, or we can write it just like this, that Vp divided by under root of 3 into voltage on the secondary side, right? We can write it just like this. And on the vice versa, if one asks you about the delta to star turns ratio, delta to star turns ratio, then it will become TR delta to Y connection. It will be the ratio between the primary turns on the primary side of a transformer to the turns on the secondary side of a transformer, and it will become under root of 3 into Vp divided by Vs. It will just like this. So you have to maintain the difference between these two types, that if there is star to delta turns ratio, then it will become Vp divided by under root of 3 into Vs, whereas if it is delta to star turns ratio, then it will become under root of 3 Vp divided by Vs. So coming on to the next point, that three phase voltage, line voltage and line current, right? We first of all we will take the primary to secondary configuration. Three phase line voltage or current, three phase line voltage or current. For this thing we will make a table. It will show that primary to secondary configuration, right? And then line voltage, that is primary or secondary, and likewise line current, it will be primary or secondary. Then if this configuration is delta to delta connection, then this VL means line voltage will equal to N into VL, where what is N? Assume that N is the ratio between turns on the secondary side divided by the turns on the primary side. It is the ratio between turns on the secondary side to the turns on the primary side, right? So this delta to delta connection in the form of voltage will be written as VL, that will be lead to NVL, where we have this value of N is given here, right? Now if we can say that this VL can then be dealt as current across the line current across this delta to delta configuration, then we can say that this IL will be lead to IL divided by, sorry, this is smaller n that we have assumed here, right? It means that NP over NS into IL. It means this expression means that NP over NS into IL. So this will be IL divided by N. Now if this configuration is modified to delta to star connection, right, then what we have this VL, it will be leading to under root of 3 dot N dot VL, right? So this will be on the primary or secondary side to the line voltage, and then when we will deal with the line current, then line current will be leading to this factor IL divided by under root of 3 dot N, right? It will be just like this thing. Then star to delta connection. What about this star to delta connection? It will become VL will become N dot VL divided by under root of 3, and then in this case IL will be leading to under root of 3 dot IL divided by N. This is basically the formula for the line voltage or line current when there is the star to delta connection. And last one is when we have this star to star connection or Y to Y connection. Then in this particular case we'll have VL will be leading to NVL and IL will be leading to IL by N. It is just like same as in the case of delta, as you can see this. Now we can say that delta to star connection or star to delta connection, it will be leading just like this, that the under root of 3, the square root of 3 will be involved in both the voltage, line voltage and line current, right? Whereas across these two across the delta to delta or star to star connections, there will be no square root of 3 involved, right? So you will keep on remember that whenever their connection will be delta to star or star to delta connection, actually why we are considering this star to delta or delta to star connections, because one is preferring the line voltage whereas the other one is preferring the line to neutral voltage, right? The line to line voltage is preferred in the one case, whereas the line to neutral voltage is considered in the other case. So that's why we have this sort of things here. Okay, so this is all from our today's lecture. We will further elaborate it in the next lecture, in which we will study the delta to delta transformer or then delta to star or star to delta connections, and afterwards we will be able to learn about the auto transformers, right? So this is all from today, and thank you very much for listening the lecture, and I'll provide you with the notes on your email. Okay, thank you very much students. Bye bye.